So we've seen now our single replacement reactions. Those are pretty good. You see a lot of that, especially with the metals. We're going to do an entire lab involving these types of reactions. So you'll get to see it more involved there. But the metals are really easy. Metals are great replacers of each other. This principle is one of the reasons why battleships work the way that they do. If you think about it, a battleship is metal being put in a salt water solution. The metal should corrode. It should turn into rust very, very quickly, but it doesn't. They use this type of single replacement reaction. They actually plate the part of the ship in zinc, and the zinc replaces the iron in the steel. And it pulls the oxygen out of the iron oxide in rust, and it leaves the iron behind to make the steel strong. So it forms zinc. So that zinc goes in, replaces iron, and grabs the oxygen, replaces the iron, and does a single replacement reaction in there. The other thing that we do the most often here are double replacement reactions. And the reason we do double replacement reactions more than anything else is, notice again, in a single replacement reaction, you must have an element. And single elements sometimes are hard to come by. Metals are pretty easy. Non-metals, not so much. It's kind of hard to come by pure chlorine. It's very hard to find pure fluorine. However, it's really easy to find silver, zinc, copper, etc. So we do a lot of things with compounds. So in a double replacement reaction, you have nothing but compounds. Compound, 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 compound. What replaces what? It doesn't matter, as long as you replace the same thing in both sides. So I like to do the first thing that's written because the positive ions are always going to be the first thing that's written. So I'm going to take the A. It's going to bump out B. B is going to jump over and form with X. So you end up with AZBX. So your positive ions from each compound switch places. It's the easiest thing to remember. Is it always a positive? I have no idea, but there's no way to prove it otherwise. So we always assume that it's always the positives. Here's a great example. Lead nitrate plus sodium chloride yields lead chloride plus sodium nitrate. Okay, so what replaced? Lead switched with sodium, sodium switched with lead to form lead chloride and sodium nitrate. Now, second place that people always get into trouble with these types of reaction stuff is remembering to balance the charge. Okay, charges don't necessarily carry from left to right. Notice the chlorine does not have a 2. It has a 1, but here it does. That's because lead is plus 2. Chlorine is minus 1. When you cross those charges, it becomes PbCl2. Okay, the nitrate had a 2. Here, it has a 1. Why? Sodium is plus 1, nitrate is minus 1. They're equal, so they cancel out. Okay, don't forget that. We will go over this extensively, and writing reactions is hands down the most important thing we do all year. Here's another example. Silver nitrate plus calcium hydroxide yields calcium nitrate plus silver hydroxide. Again, same scenario where crossing the charges is extremely important. What do you see? Compound plus compound yields compound. Oh, look at that. And another compound. So when you see a chemical reaction that involves nothing but compounds all the way through, instantaneously you know that it's double replacement reaction. Okay? Every one of them has their own unique thing. This experiment is an example of a double replacement reaction. In this experiment, you'll see in my test tube, I have a clear liquid, which is lead nitrate. On a side, lead nitrate is the only compound of lead that's soluble in water, which is why lead is so dangerous to the environment. What I'm going to do is I'm going to add some sodium chloride to it. And sodium chloride, as we know, is also known as table salt. And it's very simple, so it's a little white compound. When I dump this little white crystal compound into this, you will see immediately a reaction. And my little white compound has now become, my clear liquid has now become this milky, grainy, kind of powdery stuff. Kind of looks like a snow globe as you experiment. And you'll see that it starts to settle itself down. And what I've created in this experiment is I have created sodium nitrate, which is completely soluble. I'm going to give it a quick stir. And I've created sodium nitrate, which is completely soluble. That's the clear liquid that's forming in the experiment. And then the bottom is all lead chloride. Now, I did not put that much sodium chloride in, but you can see a considerable amount of lead chloride has been created. So it's quite a dangerous problem, the lead in the environment. This is the second example of a double replacement reaction. In this case, again, I'm starting with a clear liquid, but my clear liquid this time is hydrochloric acid, 1 molar hydrochloric acid. So to it, I'm also going to add a white compound, but instead of sodium chloride, I'm going to add sodium hydroxide, which is a tiny white tablet. So again, I'm taking a white compound, I'm adding it to a clear liquid, but this time, when the two react, you'll notice no white powder created. And I want to make sure, I use this as an example of a misconception that many people have about reactions. There is a reaction that's going on in here. The problem is the sodium hydroxide is a clear liquid. The compound that's created from this is going to be water and sodium chloride aqueous. You'll see it does kind of react. As I stir it up, there's a little bit of a reaction going on, but it's pretty much producing another clear compound because when these two substances react, they produce water and a salt, and water obviously is clear. So don't assume that just because two things are reacting, you're going to see a chemical reaction. On the reverse, don't assume that just because you don't see a chemical reaction doesn't mean something's not happening.